So the next talk is by Professor Srikanth Saripalli. The talk is on perception in the wild for off-road autonomous vehicles. Okay, so here we go. Srikanth Saripalli is a professor of mechanical engineering and director of the Center for Autonomous Vehicles and Sensor Systems at the Texas A&M University. He received his BE degree from Birla Institute of Technology and Sciences from Pilani in India in 1999, and his MS and PhD degrees from the University of Southern California in 2002 and 2007. He is a roboticist with research interests in unmanned systems in general and aerial vehicles in particular. So with that, I would give the thing over to Sri.
Thank you, Abhinav. Can you hear me?
Yep.
Okay, perfect. Thanks. I was hoping you wouldn't go through the entire description for the bio. Thanks very much. I heard Basti's talk, Basti and his research scientist. It was very interesting. So today, wanted to give a kind of like a broad overview of what we've been working for the last 2 years in terms of off-road autonomous vehicles, specifically from a perception perspective. And I wanted to motivate it by some of the challenges that we have in the field, right? So all of these are autonomous. They're basically doing GPS denied autonomy, where they're given a set of waypoints. And if you see this particular vehicle, what happens to this is it kind of says that, kind of thinks that the water is a very flat, plain area, and it starts going through those mud puddles. And before even that, it gets stuck in the quicksand over there, right? So, and quicksand's quite normal. And if you look at the imagery, it actually seems much smoother than the area around, right? So it's perception really in these off-road scenarios is challenging because you have these cases, right? And then here, again, this is autonomous, this is going to, trying to climb a slope. And if you see there's that, I never thought you could do that with a warthog, but that's interesting. And so, of course, at that time, somebody took over, but it almost tilted because you have issues with figuring out what kind of slope you can climb, and if you have rocks and things like that in the slope, right? So how do you actually come up with it? And of course, here we have a classic case where the vehicles actually, it did find the negative obstacle, but then it didn't realize how bad that negative obstacle was. And of course, there were issues with how quickly the vehicle was moving. And so you have a case where the vehicle again got high centered. Right. So I kind of just wanted to show you these to kind of motivate the problem as to what happens. And so there are questions about, so if you have mud and quicksand, how do we detect them, right? So obviously vision's not the only sensing modality that would be useful, and maybe LiDAR is even not useful if you have water. So you have to think about multiple sensors and how do you fuse them, and how do you fuse them to be actually able to detect them. Then there are questions about dynamics and stability. So it's not just enough if you detect that there's a slope or there are rocks. It's also important as to how you couple that to your planning and control pipeline, right? And then the fun part, of course, of all of this comes when your vehicle gets stuck in these situations and you have to tow those vehicles out, right? So these are hard problems and these are unsolved problems right now, right? So what I want to talk about, and I think this is a nice segue to what Dr. Scherer's talk was about, was some multi-sensor fusion datasets that we have that are available for actually developing perception algorithms. And one of the main takeaways from that would be really that the current datasets that are available specifically for off-road environments are not enough. And the current on-road datasets, the algorithms that work with other state of the art, at least in on-road datasets, are not generalizable, at least according to what we have seen on these off-road datasets, right? So that's one case. And then I want to kind of take a brief detour to talk about calibration using semantics for LiDAR and visual sensors. And then kind of think about how, if we are, so rather than thinking about the problem of perception, so given a task of driving or given a task of navigation, how can we simplify the problem so that maybe we can solve a simpler problem rather than trying to solve the entire problem, right? And then I'm happy to take questions, but really this talk is about 2.5 years of work by a lot of my students. So it's a high level talk, but I'm happy to take questions and go into specific details about each one of them, right? So this slide kind of tells you what the problems are, right? So a lack of multimodal data sets. There are a lot of visual data sets, but there's relatively very few LiDAR and say even radar data sets when it comes to off-road environment. And then of course, once you have these data sets, or once you've done once you have trained your model, there's a question of where to go with these, right? So perception is not just trying to figure out whether there's grass, whether there's slope, but in typically off-road environments, you're thinking about load-bearing surfaces, right? So really the environment might be covered by grass, and so you have to kind of think about what a load-bearing surface is and how do you estimate it. And that could be the same thing with mud and quicksand and things like that. And then of course, there's a question of how fast to go, right? So which deals with dynamics, suspension, and terrain dependent. We'll kind of not go through that for this talk because this is really about perception, but that's very, very important also. I just want to mention it over there. If I can, oops. Yeah. So here's a big list of data sets. This is probably a year old, so this is probably not comprehensive, but kind of tells you, at least in 2020, I think, what the data sets were. The top table is all on-road data sets, kind of says what the year is, number of scenes, RGB images, whether it has LiDAR or not, where it was taken, things like that. And I apologize in advance if I have not covered your data set in this. As I said, this is about 2 years old, and it was really the take home is that there are a lot of online data sets, and the bottom table kind of shows the offline data sets. So this is the YCOR, in case you're wondering, is the Yamaha off-road data set that Dr. Scherer was talking about, right? So if you look at the take home again from this that I want to talk about is, other than the Kitty and the New Scenes data set, most of the other ones are purely RGB imagery data sets, but also Kitty happens to be one of the standards with which we test. And if you look at the off-road environment data sets, almost all of them are camera-based, so there's not really a multimodal data set that you'd like to use, right? Now, of course, they're very, very useful. That doesn't mean that these data sets are not useful. It's just that if you're interested in some of the harder problems where cameras might not be the only sensor that you're interested in, then these are not the only data set. So one of the first things that we did is we collected a data set in our campus, which is an off-road campus called Relief. It has grass, mud, puddles, some kind of gentle slopes, things like that. It's synchronized, so the LiDAR and camera images are synchronized with GPS and IMU, and it's annotated, right? So what you see here is the top images kind of show the raw images. The middle ones show the image labels for them. And the bottom ones show the point cloud, and the point clouds being annotated, right? So the reason, and we actually published this data set, this is an ICRA paper from last year, and it's free to use for everybody. But we took sufficient time. We actually went to a commercial company, so that Figure 8, so that we could do the image labeling and the point labeling with sufficient accuracy, right? And also, one of the things that I wanted to talk about on this is we went through a significant amount of work to actually present benchmarks of this with the state of the art, at least in 2019, 2020, with the state of the art on-road semantic classification work. right? So kind of shows you what kind of labels we have. So we had about 20 classes, so things like dirt, grass, tree, pole, different kinds of classes. And a lot of the classes came from a previous data set that was published by the Army Research Labs called Rugged. So we kind of said, instead of coming up with our own class nomenclature, we used the nomenclature. So in the sense, somebody could use a previous data set, work on it, and then use our data set so that it helps them and then gives them a much more larger set, right? So again, one of the things that I wanted to show from this data set is, if you look at it, there is a large class imbalance. So sky, grass, tree, and bushes take a large amount of space, and then similarly, that's both for images and point cloud distributions, right? So there's a large class imbalance between what you see in this data set in terms of the number of classes. But if you kind of think about it from a perception perspective or a planning perspective, it's easy to kind of segment out grass and tree and bushes. Kind of things that you're interested in are probably puddles and fences and things like that. So again, the take-home message here is, while we have this data set, once we've collected the data set and we've annotated the data set, kind of realize that we need to collect more data, and that data needs to be in these classes, really, if you want if you want this data set to be truly representative of what is happening, right? And at the bottom, the table 4, which you see, kind of says what, at least again, 2018, 2019 algorithms, how they perform on the RELS 3D data set compared to something like the Cityscape data set. Right? And again, the point being that these algorithms are fairly good, but they're not generalizable to off-road environments, at least the standard algorithms that are there, right? So again, this is for the left table is for image, and the right one is for point cloud segmentation, right? Really, it would be nice if we can generalize these algorithms and use these algorithms, right? So let me play this. It kind of gives you, I won't go through the entire video, but it kind of gives you an idea of the setup. So we have a warthog. This is approximately where we were doing it. And what you see here is on the top right, you see the image. The bottom right is the annotated image. And then the left is the point cloud, the annotated point cloud that you have from this, right? And this goes on. I think this is one of the trails in which we were running the vehicle. And of course, you see people walking behind it because this is manual. And so there are multiple trials of this running. And this is, again, in the interest of time, I'm not going to go through the entire video, but it kind of shows you what the ground truth is, what the prediction from at least 2 of the state-of-the-art models at that time were, kind of gives you an idea. And again, this is all available on GitHub, and folks have been using it quite a while. So this is useful for actually developing models and then validating them, and then analyzing them, right? So the other thing I think that we wanted to do was, yes, that's for semantic, but we also wanted to analyze visual inertial odometry algorithms, right? So one of the things that we did is we collected, again, synchronized data in fairly rugged environments, and then we analyzed, again, that data. So this is vision data and IMU data, IMU data being at a fairly high update rate, 400 Hertz, synchronized with vision data. And we analyzed it on OpenVINS and VINS Fusion to kind of see what, where these algorithms, how well do these algorithms work. Again, this is published, so folks can actually use this data to develop algorithms for both visual inertial odometry. And so I think this is, again, another data set which shows kind of that there's grass, there's lots of variation in slopes, there's lots of lots of pitch angle variation. So there's some, again, I won't go through the entire data set, but it kind of gives you, this is again, I'll provide the GitHub links at the end, but this kind of shows how these data sets can be used for evaluating and analyzing the state of the art, either visual odometry or semantic algorithms, right? So as I mentioned, one of the things, so if you think about it, your on-road scenes are well structured and have a fairly balanced class distribution. At least what we've seen in our limited collection of data is that we have strong texture and we have unbalanced class distributions, right? So one of the things that we were wondering was how can, so instead of trying to classify the entire image, what if we were interested in classifying the image for a specific task as, say, a sky, a non-traversable region, and a traversable region, right? And in the traversable region, then thinking about classifying it, subclassifying it into smaller tasks, right? So the idea being, so can we take something like the RELIS 3D dataset or the rugged dataset, and then it has 20 classes or 25 classes or 30 classes. But really, if you're interested in the navigation problem, you don't care about most of the classes, right? What you care about is what are the places where I can't go, right? So non-traversable regions. Are there any obstacles that I should be aware about? And then in the traversable regions, are there any interesting things that I'm interested in, right? So what you see here is there is a mud puddle. This is definitely a traversable region, but there is a puddle that you're interested in. There are some obstacles here, like you see poles and things, and there are non-traversable region, and there's a large amount of sky that is there, right? So if I run this, and if I run this, right? In the interest of time, I know I have 25 minutes, so I'm not going to go through the entire video, but what it's showing is, can you take the classes, can you pool them up, pool them into a smaller set of classes? Can you run a semantic segmentation algorithm of that? And then once you've got the traversable region, then we use a color-based segmenter so that we can then segment it out into different various instances in the traversable region, right? So we are interested. So if it's sky, we don't care what's in the sky. If it's non-traversable region, we don't care what there is. If there are any obstacles, we do care about them. But in the traversable region, we're very interested if there are rocks or mud or gravel and things like that, right? Now, we've done this with imagery, right? But of course, the harder problem is, can you do something like this by combining imagery with LiDAR data? And then can you use that in real time, right? So we haven't got there yet. This is some of our initial work in doing this and with imagery. Right. So to do this combination of LiDAR and imagery, one of the things that you want is calibration, right? And as we were looking at calibration, there are many methods of calibration. Typically, calibration is considered kind of like an offline process that you do before you go and collect data, right? But as we all know, when we do robotics, we go collect data. We either have a calibration that we come back to the lab and then we say, oops, we don't have a better calibration. It would be so great if we had nicer calibration. Or something happens, somebody kind of bumps into a camera or while taking it out somewhere or something like that, something changes, and then we come back, or we look at our SLAM or we look at our imagery and we kind of say, well, the calibration is not great. I wish if the calibration was great and I could put these things together, right? So one of the things that we were interested in was to kind of look at the entire calibration, and this is kind of like a broad way of looking at calibration. There's targetless, online, learning, and non-learning based calibration methods, and kind of ask the question, we get data, let's say you have imagery data and you have LiDAR data, and then you've collected the data, you've basically done a semantic labeling of this data. And then you come back and you realize, wouldn't it be nice if I'm able to recalibrate based on the data that I have, right? And sometimes it works. Sometimes if you believe that your semantic labeling is good, then of course your calibration will be better. If your semantic labeling is bad, then of course this method doesn't give you the greatest calibration. But it's a nice way to kind of say, look, I've done this, and now I have this offline data set. Now can I actually make semantic calibration of this, right? So we use mutual information, which is very used in normal calibration, right? So the idea basically is to take your point cloud from LiDAR coordinates and then project it into the camera coordinate frame. Kind of know the field of view of the camera, you kind of know the LiDAR field of view, sample images, semantic labels from there, sample the LiDAR semantic labels, and then basically solve an optimization problem, which is calculating the rotation and the translation between them. Right. So this is the initial step that gives you the initial rotation and translation. And then, of course, you can refine it. We believe that we have an interesting method of refining it where we use a neural network-based mutual information, which is differentiable. And so that has some nice properties on how you can use that and how you can differentiate it so that you could get better calibration, right? So what I wanted to show was this is our data set Relis 3D. This is a different way of semantic calibration called SUUE. This is based on some work that comes out of University of Michigan, based out of mutual information, 2D mutual information. We actually modified it so that we can use it with ours. So we call it PMI, right? And sorry, this is our work. This is our offline calibration that we got before we collected the data, right? So if you see this, I'm not sure if you can see this. You could go onto the website and look at it again, the GitHub. But you can see that using the calibration that we have, the LiDAR, so what you're seeing is the LiDAR data projected on the image data. And you can definitely see at some places where the projections are not the greatest, right? And we show that over here where the projections are not the greatest. And so basically what we want to say is that if you have good labels, or you can go back and make the labels better, right? Because it's an offline process, using something like this gives you a calibration that can be used for doing things, right? Again, we do this with Kitty dataset also. It should say Kitty here. It says Relis 3D, right? So this is the role pitch yaw data that comes from Kitty. So kind of if you want to say that's the ground truth. This is SOIC, this is PMI, and this is ours. So again, if you look at this picture where I have my mouse, so this is the Kitty dataset where there's offset in this. This is SOIC where the LiDAR and the imagery are not, and this is the 2D based mutual information, and this is using mutual information and then refinement on that, right? So what this does is, given that you have semantic labels for both LiDAR and imagery information, you could use those semantic labels to come up with a better offline calibration that can be used for other tasks, right? And finally, given that I am almost out of time, so one of the things that we want to look at is, again, so I've talked about data sets. I've talked about how we could use those, some of the imagery data sets to do a simpler segmentation. Then I've talked about calibration. So the final thing is, can we now do this on LiDAR data sets, right? And so the broad idea for this is, there are data sets such as Semantic Kitty, and there is a Semantic POSS data set. And both of them, there are models that are trained on them. But of course, we are really interested in using those models in an offline environment, right? But the broad idea is there are some features that are similar from an on-road to an on-road. And then there are some features that are completely different from an on-road data set to an off-road data set, right? So can we extract these shared features, and then can we learn these private features? And can we use them together to come up with a better segmentation from LiDAR, right? Again, these are initial results. So So this is purely for domain adaptation. And the idea is we have a data set that we call Semantic Unmanned Systems Lab. So it's purely LiDAR data set that is collected in both on campus at Texas A&M and off campus at the ROF. It's a fairly tiny data set, right? And then there's, of course, Semantic Kitty data set, and then there's Semantic POSS data set, right? And our interest really is, can we train on Semantic Kitty data set? And then what happens when we test it? Can we use the features that we have trained on Semantic Kitty data set? And then if we transfer them to our data set, how well do these work on both our data set and also the Semantic POSS data set, right? So again, this is on GitHub, so I won't go through the entire thing. I'll stop, and then I'll go through maybe a couple of these, and then I'll stop after that, right? So what you see here is the model A is AlphaNext, trained on Semantic Kitty. B is the same model trained on Semantic Kitty, but adapted to Semantic POSS. And the C, which you see here, is model trained on Semantic Kitty and adapted to Semantic USL. And then here, what you see are each one of our data sets. So first one is Semantic Kitty data set. The second one is a prediction of the model A on Kitty, and then so on and so forth for each one of them. I know this is a confusing video, and to go through the entire video in this format. But really, the question that we are asking is, given that there is a large amount of on-road data and large amount of trained semantic networks, can we use them to adapt them to off-road data, right? And so I am going to stop here, but I just wanted to put this video so that you see what it takes to actually, when things get stuck. And I have the papers that are here, which and the GitHub for each one of them, so that you could go look at it, and I'm happy to take questions. Thank you.
Thank you for the talk, Sri. So are there any questions? You can either raise your hand or enter questions on the chat. Maybe in the meantime, I can ask a question. So that's really interesting how you put it in terms of off-road to on-road. Was wondering, so do you only do this for classes that are overlapping, right?
Yes, because if it's a completely new class, then we have no information on those classes, and so we can't do anything on that. So it kind of is an unknown class.
Does it say an unknown class, or does it predict it as one among the known classes?
So if we have a small number of off-road data also, and if there's a class that is there, then it's supposed to predict it. But right now, if you look at the paper, our mean IOUs are in, I believe, in the 50–60%, same as, so there's a good chance that it won't predict it also, right? And it can mislabel it also. So definitely, there's a lot of work that needs to be done. I mean, as you very well know, on the LiDAR side, there's a lot of work that needs to be done on the LiDAR semantic segmentation. And I think one way to think about it broadly is not to think about purely LiDAR, but to think about how you can, because there's a lot of work on the imagery side. How can you do that? And that's why we were looking at the calibration. So in a sense, we wanted to cheat by saying, can you use a lot of things that are on the image side, and can you somehow do that on the LiDAR side, right? But then projections, you lose some information, but maybe that's okay, right? Again, depends on what you want to do.
Okay, any more questions? Maybe I have another question, but I don't want to keep asking questions. But if there's if somebody else has question, they can ask. In the meantime, maybe again in the domain adaptation thing. So is RELIS 3D? I don't remember if it's the same number of LiDAR scan lines as Semantic Kitty and the other one.
No, I think RELIS 3D is 64. We used the Auster 64, and if I remember, Semantic Kitty was 128. Yeah, Velodyne 128. I don't remember what Semanticity is. So, but Semantic POSS was from KAIST, I think, and that's a completely different LiDAR. So there are issues with that also, right? So when you get down to it, yeah, so the rings and how they are and things like that, there are issues with that. Yes.
So did you have, I guess, my question was, did you have anything specific that you dealt with to go from like a dense to a sparse LiDAR in this case?
Well, not, I mean, 64 and 128, we didn't actually think, no, I don't think. I'll have to ask my student, but on top of my head, I don't think we did any specific things to go. But of course, if you went to a 16 channel, like a VLP 16 or something, I would assume that you have to do something because it's very sparse. And that's, so one of the things that we are interested in is to look at these newer LiDARs from DJI, which are random instead of having the same scan pattern. So those are interesting because you could, if you're going slow enough, you actually get a lot more data. They're also much cheaper, like the Horizon LiDARs are only $1,000, $2,000 compared to any of the Velodynes and things like that. We haven't used them, but it seems interesting to use these random scan pattern LiDARs, particularly if you're going slow or if you're revisiting the same location, because your Ousters and Velodynes and things like that, they're scanning the same area. So you're there for an hour and you still get the same point cloud. While if you have random access, then an hour gives you a lot more data, hopefully equivalent to what you'd get from a camera or something like that. Anyway, I don't see any other questions, so.
I guess.
Srikanth, if it's okay, I would have another question.
Yes, please.
What is your intuition for these situations, like the slow P environments or these mud surfaces or quicksand?
Yeah.
Like, do the current sensor combinations even offer us like any good solution, or is this still just, I don't know, try to recognize it visually and then stay away from it?
So quicksand, I think, is the hardest. I don't think vision actually works and LiDAR fails. You have to use something like ground penetrating radar. But I mean, think about people. I mean, that's why it's called quicksand. I mean, people get stuck there. So maybe that's more you get stuck there, then you learn that, but it's hard because, right? But I think that the slope, ruggedness, I think a combination of IMU plus LiDAR plus vision, and I'm going to give a plug to Abhinav's paper here. I was on using sound, I believe. I don't remember the exact paper. IMU in off-road environments, learning, and maybe Abhinav can say that, which is using the sound to figure out where you're going and then going forward. This is Wolfram and Abhinav's paper.
And using that for vision, that paper you mean?
Yeah,
so there's two. I think one we did only with sound, and another one we used the vision as a supervision for the audio as a supervision to the visual classifier.
Yeah, so I think you definitely need multimodal, but you need sufficiently different multimodal. So I would say audio is something and IMU is something. Maybe audio is not the right thing, but definitely you want to find something that's not in the same class as visual or LiDAR, and then use that, because that gives you, and IMU is a good one, but IMU alone is probably not enough, and use that as a supervisor for your visual and LiDAR. Right. And particularly, I think, I think that's true for agriculture, that's true for construction, that's true for these. There are always going to be cases that we haven't seen. So, right, yeah.
Oh, thank you, Srikanth.
Thank you.
Okay, I think we are out of time, actually. Yeah, okay, we have a few more minutes. Is there any questions? Okay, I don't think so. I would like to thank Sri, as well as Basti and Venshan for this talk.